Hello and welcome to Boring Physics for Sleep. Tonight we are going to dive into a concept that seems simple but hides a fascinating layer of physics: why heavier objects do not fall faster than lighter objects in a vacuum. You might have heard this before, perhaps attributed to Galileo, but understanding the mechanics behind it requires us to slow down, relax, and think about two of the most fundamental concepts in all of classical mechanics: gravity and inertia. We will keep the pace slow and the details precise. Close your eyes, let the uniform tones and the steady rhythm of the concepts wash over you. The common, intuitive belief is that if you drop a bowling ball and a feather, the bowling ball will hit the ground first because it is heavier. And if you do this experiment right now in your room, the bowling ball will, in fact, win the race by a massive margin. But this is where physics gets interesting. Our real-world experience is dominated by an invisible, yet powerful, force that complicates everything: air resistance, or drag. If we could eliminate the air, say by dropping the bowling ball and the feather inside a giant vacuum chamber, they would both accelerate downwards at the exact same rate and hit the floor simultaneously. This is the core of tonight's deep dive. We need to understand why the force pulling the heavier object is proportionally larger, but its resistance to acceleration is also proportionally larger, resulting in a perfect cancellation that makes the acceleration identical for all masses. Let's begin with gravity. What is gravity? In the simplest terms, gravity is an attractive force that exists between any two objects that have mass. The force of gravity that the Earth exerts on an object is what we commonly call the weight of that object. Sir Isaac Newton formalized this force with his law of universal gravitation. He stated that the gravitational force, which we can call F sub g, is directly proportional to the product of the two masses and inversely proportional to the square of the distance between their centers. The formula for this universal gravitational force is F sub g equals g multiplied by m sub 1 multiplied by m sub 2 all divided by r squared, where F sub g is the gravitational force between the two objects. G is the gravitational constant, a fixed number. M sub 1 is the mass of the first object, say the Earth. M sub 2 is the mass of the second object, say the falling object. R is the distance between the centers of the two masses. Now, let's focus this specifically on an object falling near the Earth's surface. When we talk about the weight of an object, we are calculating the gravitational force acting on it. Since the mass of the Earth, m sub 1, and the distance from the center of the Earth to a point near the surface, r, are essentially constant for any object we drop, we can group the gravitational constant g, the Earth's mass m sub 1, and the radius r squared into a single constant. We call this constant g the acceleration due to gravity. The value of g near the Earth's surface is approximately 9.8 meters per second squared. So, the weight of an object, which is the force of gravity acting on it, simplifies to a much easier formula. F sub g equals m multiplied by g, where F sub g is the gravitational force or the weight. M is the mass of the falling object. G is the acceleration due to gravity, 9.8 meters per second squared. This formula is the first critical piece of the puzzle. It tells us that the gravitational force, the weight, is directly proportional to the mass of the object. A bowling ball with twice the mass of a tennis ball will experience twice the gravitational force, or twice the weight. This confirms our intuition: heavier objects are pulled down with a greater force. So, if the heavier object is pulled down with a greater force, Why does it not fall faster? This brings us to the second critical concept, inertia and Newton's second law of motion. Newton's second law is the most important equation in classical mechanics. It describes how a force causes an object to accelerate. The law states that the net force, F sub net, acting on an object is equal to the mass of the object, m, multiplied by the acceleration, a, that the force produces. The formula is F sub net equals m multiplied by a. This equation can be rearranged to solve for the acceleration, which is our goal. We want to know the acceleration of a falling object. Acceleration equals F sub net divided by m, where a is the acceleration. F sub net is the net force acting on the object. M is the mass of the object. Now, let's consider an object falling in a complete vacuum, where the only force acting on it is the gravitational force, F sub g. In this ideal scenario, the net force, F sub net, is equal to the gravitational force, F sub g. We can substitute our expression for the gravitational force, F sub g equals m multiplied by g, into the acceleration formula. First, the definition of acceleration. A equals F sub net divided by m. Second, replacing F sub net with the force of gravity, F sub g. A equals F sub g divided by m. Third, replacing F sub g with its definition, m multiplied by g. A equals m multiplied by g divided by m. And here is the magic moment. Notice the term m, the mass of the object, appears in both the numerator and the denominator of the equation. Any term that appears in both the numerator and the denominator of a fraction can be cancelled out. The mass m cancels the mass m. A equals g. This is a profound result. The equation for the acceleration of a falling object in a vacuum, A, simplifies simply to g, the acceleration due to gravity. The mass of the falling object, m, has completely disappeared from the final equation. This means that the acceleration of any object falling in a vacuum is 9.8 meters per second squared, regardless of its mass. The bowling ball and the tennis ball both accelerate at 9.8 meters per second squared. They gain speed at the same rate, and therefore, they hit the ground at the same time. Let's step back and consider why the mass cancels out. This is the crucial conceptual leap that connects the two halves of the puzzle. When we look at the rearranged equation, acceleration equals F sub g divided by m. The numerator, F sub g, is the force of the pull, the weight, which is directly proportional to the mass. This is the source of the acceleration. Heavier objects have a proportionally larger F sub g. The denominator, m, represents inertia, or the object's resistance to being accelerated. The mass is the measure of an object's inertia. Heavier objects have a proportionally larger m. Think of it this way. A heavier object, the bowling ball, has a stronger pull from gravity, which is F sub g. But that same bowling ball also has a stronger resistance to changing its motion, its inertia, m. The greater pull is perfectly countered by the greater resistance. The ratio of the pull to the resistance, F sub g divided by m, remains constant for every object. That constant ratio is g. This is why physicists often use the terms gravitational mass and inertial mass. The gravitational mass is the m we use in the weight formula, F sub g equals m sub gravitational multiplied by g. It measures how strongly an object interacts with the gravitational field. The inertial mass is the m we use in Newton's second law, F equals m sub inertial multiplied by a. It measures how much the object resists acceleration when a force is applied. In all classical mechanics, these two masses are considered to be exactly equal. This is called the principle of equivalence. If gravitational mass and inertial mass were not equal, the m terms would not perfectly cancel out, and heavier objects would indeed fall faster or slower than lighter objects. However, countless experiments, performed with incredible precision, have confirmed the principle of equivalence. The measure of how much gravity pulls an object is perfectly equivalent to the measure of how much that object resists being accelerated. Let's return to the real world and the experiment you performed in your room with the bowling ball and the feather. This is where we bring back air resistance. Air resistance, or drag force, is a force that opposes the motion of an object through the air. The drag force, F sub d, depends on several factors. The density of the air, the speed of the falling object, the shape and cross-sectional area of the object. A crucial point is that air resistance does not depend on the mass or weight of the object. It depends primarily on the object's size and shape. When the bowling ball and the feather are dropped in air, both forces are at play. The constant downward force of gravity, F sub g. The upward, opposing force of air resistance, F sub d. The net force acting on the object is now the difference between these two forces. F sub net eq. Joule's F sub g minus F sub d. As the object falls and its speed increases, the air resistance force, F sub d, also increases. Eventually, the object will reach a speed where the upward air resistance force becomes equal to the downward gravitational force. When F sub d equals F sub g, the net force, F sub net, becomes zero. F sub net equals 0. According to Newton's second law, if the net force is 0, the acceleration, a, must also be 0. A equals F sub net divided by m equals 0 divided by m equals 0. When the acceleration is 0, the object stops speeding up and continues to fall at a constant, maximum speed. This constant speed is called the terminal velocity, v sub t. The equation for terminal velocity is complex, but we can look at the factors that determine it. An object reaches terminal velocity when its weight, F sub g, is balanced by the drag force, F sub d. F sub g equals F sub d. Or m multiplied by g equals c multiplied by a multiplied by v sub t squared, where m multiplied by g is the weight. C is a combination of the drag coefficient and air density. A is the cross-sectional area. V sub t is the terminal velocity. The bowling ball has a very large weight, F sub g, due to its large mass m. Therefore, it requires a very large air resistance force, F sub d, to balance its weight. The bowling ball must fall to a very high speed, a very high terminal velocity, to generate that required drag force. The feather, however, has a tiny weight. It only takes a tiny air resistance force to balance its weight. Because the feather also has a relatively large surface area for its small mass, it generates that tiny required drag force at a very low speed. The feather reaches its terminal velocity of only a few feet per second almost immediately after being dropped and falls slowly at a constant speed. the bowling ball keeps accelerating until it reaches a much higher terminal velocity, likely hitting the ground before air resistance can slow it significantly. Therefore, the reason the bowling ball falls faster in the real world is not because it is heavier, but because its high mass-to-surface area ratio makes the effect of air resistance negligible compared to its weight. The air resistance has a much more significant effect on the lightweight, large surface area feather. This principle is what allows a skydiver to control their fall. By changing their body position, they change their cross-sectional area, A, which changes the air resistance, F sub d, and thus changes their terminal velocity, V sub t. To summarize the key takeaway for this segment, the difference in how objects fall in the real world is due to air resistance. In the absence of air resistance, the two fundamental truths of physics, that gravity pulls harder on more massive objects, and that more massive objects resist acceleration more strongly, cancel each other out perfectly, leading to the elegant conclusion, all objects accelerate due to gravity at the same rate, 9.8 meters per second squared. Rest now, and contemplate the perfect balance between pull and resistance, between gravitational mass and inertial mass. I will continue the script now, focusing on the historical context and the significance of Galileo's work. The understanding that all objects fall at the same rate represents a significant turning point in the history of science, a moment when observational evidence and logical deduction finally broke free from centuries of philosophical dogma. To appreciate the magnitude of this discovery, we must momentarily step back into the classical world, specifically to the ideas of Aristotle. Aristotle, the great Greek philosopher who lived in the 4th century BCE, taught that the natural state of motion for objects was to move toward their natural place. For earthly objects, the natural place was the center of the earth. Crucially, Aristotle posited that heavier objects contain more of the element earth, and therefore, they are more strongly drawn to the center of the earth. From this, he concluded that the speed of a falling object is directly proportional to its weight. In simple terms, an object 10 times heavier than another would fall 10 times faster. For nearly 2,000 years, this Aristotelian view was accepted as absolute truth. It aligned with common sense. You drop a stone and a leaf, and the stone clearly falls faster. The influence of air resistance, though observed, was misinterpreted. It was seen as a factor, but not the primary cause of the difference in falling speeds. The inherent difference in weight was believed to be the fundamental cause. This brings us to Galileo Galilei, an Italian astronomer, physicist, and engineer who is often referred to as the father of observational science. Galileo lived in the late 16th and early 17th centuries. He was not satisfied with philosophical pronouncements. He believed in the power of experimentation and mathematical analysis. While the story of Galileo dropping cannonballs and musket balls from the Leaning Tower of Pisa is famous, it is likely apocryphal. While he may not have performed the public demonstration from the tower, his work conclusively demonstrated the fallacy of Aristotle's claim. Galileo's true genius lay not in the simple act of dropping objects, but in his thought experiments and his careful use of inclined planes to slow down the action of gravity, making it measurable. Let's explore one of Galileo's most famous thought experiments, which beautifully demolishes the Aristotelian idea. Imagine we have two objects. Object A is heavy, say a 10-kilogram cannonball. Object B is light, say a 1-kilogram musket ball. Aristotle's theory predicts that object A will fall significantly faster than object B. Now, let's take object A and object B and tie them together with a piece of string. This forms a new composite object, call it object C, with a total mass of 11 kilograms. According to the Aristotelian view, since object C is the heaviest, weighing 11 kilograms, it should fall even faster than the 10-kilogram object A. But what happens at the moment they are falling? Object B, the 1-kilogram ball, is the lighter component. According to Aristotle, it would be a slower falling object. When tied to the faster falling object A, the slower object B would act as a drag or a brake on object A. Therefore, the combination, object C, should fall at a speed slower than object A alone. We now have a paradox. The Aristotelian premise leads to two contradictory conclusions. Since object C is 11 kilograms, it should fall faster than the 10-kilogram object A. Since object C contains a 1-kilogram component that falls slower, it should fall slower than the 10-kilogram object A. Galileo recognized that the only way to resolve this logical contradiction is if the original premise is false. The only way for the combination to be logically consistent is if the speed of fall is independent of weight. If object A and object B both naturally fall at the same speed, then joining them together will not cause one to speed up or slow down the other. They will continue to fall at that same speed. This profound logical argument demonstrated that the acceleration of a falling body must be constant and independent of its mass. To measure this acceleration, Galileo used inclined planes. Dropping objects is simply too fast to measure accurately with the limited timekeeping instruments of the 17th century. By rolling balls down a smooth ramp set at a shallow angle, he effectively diluted the force of gravity, slowing the motion significantly. He could then accurately measure the time it took for the ball to cover certain distances. His experiments led him to discover the kinematic equations that describe uniform acceleration. Galileo observed that the distance traveled by a ball rolling down an inclined plane was proportional to the square of the time taken. Distance is proportional to time squared. If we let d be the distance traveled and t be the time taken, we can write d is proportional to t squared. This is the key signature of constant acceleration. He found that no matter the mass of the ball he used, the relationship between distance and time remained the same, confirming his thought experiment that all masses accelerate at the same rate. This constant rate is what we now call g. Galileo's work shifted the focus from the intuitive concept of weight to the mathematical concept of acceleration. He established that when studying motion, the critical factor is not the force itself, but the rate of change of velocity that the force produces. This paved the way for Isaac Newton. Newton took Galileo's work on acceleration and combined it with the concept of universal gravitation to create his three laws of motion, which formalized the entire system. The key takeaway from this historical interlude is that the realization that heavier objects do not fall faster was not a minor correction to an old theory. It was a revolutionary break from a 2,000-year-old worldview, transitioning physics from philosophical speculation to the realm of precise mathematical and experimental science. This transition is essential because it sets the foundation for our entire modern understanding of the universe. As we move on, we will dive deeper into the forces at play, specifically revisiting the relationship between mass, weight, and the elusive force of air resistance in greater detail. Let us now settle back into a deeper analysis of the forces involved, extending our earlier discussion on air resistance. We must be precise about the terms we are using. We have established that mass, m, is an intrinsic property of an object. It is a measure of the amount of matter in an object, and also a measure of its inertia, its resistance to changes in motion. The standard unit of mass in the International System of Units, or SI, is the kilogram. Weight, F sub g, is a force. It is the force of gravity acting on an object's mass. The standard unit of force, including weight, is the Newton. An object's mass is the same whether it is on Earth, the Moon, or in deep space. Its weight, however, changes depending on the gravitational pull of the body it is near. The relationship, as we have reviewed, is weight equals mass multiplied by g. F sub g equals m multiplied by g. On Earth, 1 kilogram of mass has a weight of approximately 9.8 newtons. When an object falls through the air, it is not accelerating at the full value of g for the entire duration of its fall. The object's acceleration constantly decreases as it speeds up, due to the increasing drag force. The drag force, F sub d, is complex, but the primary factors affecting it are summarized in the general drag equation. We will not use the full equation, but will focus on its key dependencies. The drag force is proportional to the square of the velocity. F sub d is proportional to v squared. This means if the object doubles its speed, the drag force increases by a factor of 4. If the speed triples, the drag force increases by a factor of 9. The drag force is also proportional to the cross-sectional area of the object, A. This is the area of the object projected onto a plane perpendicular to the direction of motion. This explains why a flat sheet of paper falls much slower than a crumpled ball of the same paper. The crumpled ball has a much smaller cross-sectional area. The drag force is also proportional to the density of the fluid, or air, which we can call ρ. And finally, the drag force is proportional to the drag coefficient, C sub d, which is a dimensionless number that incorporates the object's shape and texture. A perfectly smooth sphere has a lower drag coefficient than a rough, irregular shape. The effect of air resistance is to constantly reduce the net downward force on the falling object. The instantaneous acceleration of the object is given by A equals F sub net divided by m. And since F sub net equals F sub g minus F sub d, A equals F sub g minus F sub d all divided by m. Substituting the weight term, A equals m multiplied by g minus F sub d all divided by m. Now, we can separate this fraction into two terms. A equals m multiplied by g divided by m minus F sub d divided by m. A equals g minus F sub d divided by m. This equation is the key to understanding the real-world difference in falling times. The term g is the constant acceleration due to gravity, which is the same for all masses. The term F sub d divided by m is the deceleration caused by air resistance. For two different objects, say our bowling ball and our feather, they start with the same acceleration, g. But as they speed up, the deceleration term, F sub d divided by m, becomes larger. Consider the bowling ball, which has a small cross-sectional area A compared to its very large mass m. The drag force F sub d is relatively small, but the mass m in the denominator is very large. For the bowling ball, F sub d is small, m is large. The ratio F sub d divided by m is very small. Therefore, the acceleration A remains very close to g. The bowling ball continues to accelerate rapidly. Consider the feather, which has a relatively large cross-sectional area A compared to its very small mass m. The drag force F sub d quickly becomes significant, and the mass m in the denominator is very small. For the feather, F sub d is significant. M is very small. The ratio F sub d divided by m is very large. The large deceleration term, F sub d divided by m, quickly subtracts from g. The acceleration quickly drops to 0. This is the point where the feather reaches its terminal velocity. The feather's slow fall is a consequence of its low mass-to-surface area ratio. It is not a demonstration of a physical law that states lighter objects fall slower. It is a demonstration of the significant role of fluid dynamics, the study of air resistance, in real-world motion. If we were to drop a very dense, heavy object with a huge cross-sectional area, such as a large, flat sheet of metal, it would fall much slower than a small, dense pellet of the same material, even though the sheet of metal is much heavier. This is a clear indicator that area and shape are more critical to falling time in air than weight is. The key is the ratio. The acceleration is always trying to be g, but it is constantly being reduced by the drag force divided by the inertial mass. We will next explore the implications of the principle of equivalence in the context of modern physics, connecting this simple falling behavior to Einstein's general relativity. The principle we have discussed, that gravitational mass equals inertial mass, is so fundamental and has been confirmed with such extraordinary precision that it forms the foundation of one of the most important theories of the 20th century, Albert Einstein's general theory of relativity. Einstein elevated the principle of equivalence to a foundational tenet. He asserted that a gravitational field, like the one that pulls objects toward Earth, is completely indistinguishable from an accelerated frame of reference, such as a rocket that is constantly accelerating in deep space far away from any gravity. Imagine you are inside a windowless elevator in deep space. If the elevator is not moving, you would float weightlessly. Now, imagine a powerful winch begins to pull the elevator upward with a constant acceleration of 9.8 meters per second squared, the value of g. If you stand on a scale in the accelerating elevator, the scale would read your normal Earth weight. If you drop a ball, it would appear to fall to the floor with an acceleration of 9.8 meters per second squared, exactly as it would on Earth. There is no experiment you could perform inside that elevator that would tell you whether you are A. standing still on the surface of the Earth, or B. accelerating at 9.8 meters per second squared in deep space. This is the equivalence principle as stated by Einstein. The effects of a uniform gravitational field are the same as the effects of a uniform acceleration. This profound equivalence led Einstein to an entirely new model of gravity. Instead of gravity being a mysterious force that acts instantaneously across space, as Newton described, Einstein proposed that gravity is not a force at all, but a manifestation of the curvature of space-time. According to general relativity, massive objects, like the Earth, do not generate a force that pulls other objects toward them. Instead, they warp the fabric of the universe, a four-dimensional entity called spacetime, much like a bowling ball placed on a stretched rubber sheet would create a dip. When a lighter object, like our falling feather, approaches the Earth, it is not being pulled by a force. It is simply following the shortest, straightest possible path, a geodesic, through the curved spacetime around the Earth. This curved path, which is the shortest distance between 2 points in curved space, appears to us as the object accelerating toward the Earth. The elegance of this model is that since the curvature of spacetime is the same for all objects, regardless of their mass, follow the same path. Imagine two marbles rolling side by side toward a dip created by a bowling ball on a rubber sheet. They both follow the same curve into the dip. It does not matter if one marble is heavier than the other, the curvature of the sheet is already set by the massive bowling ball, and the marbles simply respond to that curvature by following the same path. This conceptual shift provides an even deeper justification for why all objects fall at the same rate. In Newtonian terms, it is a coincidence that the gravitational mass perfectly equals the inertial mass, causing the mass m to cancel out. In general relativity, it is a necessity of the geometry. Gravity is not a force that varies with the falling object's mass, it is the geometry of the space the object is traveling through, and all objects must travel through that same geometry. The concept of mass itself is thus split into two roles, yet remains a single, unified quantity that determines both the extent to which an object warps spacetime, its gravitational influence, and how it responds to that warping, its inertial resistance. This principle is so fundamental that a violation of it, finding even a slight difference between gravitational mass and inertial mass, would dismantle the general theory of relativity. Experiments continue to test the equivalence principle to astonishing precision, finding no deviation. The acceleration of a falling object remains constant. We have now traveled from Aristotle's initial intuition, through the experimental and logical genius of Galileo, to the unification of gravity and inertia by Newton, and finally to Einstein's geometric interpretation of the universe. The simple question of why a heavier object does not fall faster is a gateway to the deepest secrets of physics. The answer is a quiet declaration of the profound order and balance of the cosmos. The greater pull on a more massive object is precisely and perfectly nullified by its greater resistance to acceleration, leaving all objects to fall at the same, constant acceleration in a vacuum. Let us conclude this segment by reviewing the formulas we have utilized and focusing on the precision of the acceleration due to gravity, g. The two primary formulas that govern this entire discussion are Newton's law of gravitation as applied to weight, and Newton's second law of motion. Newton's gravitational force, or weight. F sub g equals m multiplied by g. This tells us that the force of gravity pulling an object down is directly proportional to its mass, m. Newton's second law, solved for acceleration. A equals F sub net divided by m. This tells us that the acceleration produced by a force is inversely proportional to the object's inertial mass, m. The unification of these two formulas, under the condition that F sub net is F sub g, is what leads to the cancellation of mass. A equals m multiplied by g divided by m equals g. The acceleration of a falling object is g. The value of g is commonly stated as 9.8 meters per second squared. However, the exact value is not a universal constant like the gravitational constant g. The value of g varies slightly depending on two main factors, altitude and latitude. First, altitude. Since the Earth is not a perfect sphere but an oblate spheroid, it bulges slightly at the equator, and the law of universal gravitation includes the square of the distance. The value of g is slightly lower at higher altitudes and higher on mountain tops. Since the distance from the center of the Earth is greater at higher altitudes, the gravitational force, and thus the acceleration g, is slightly reduced. Second, latitude. There are two reasons for the variation based on latitude. The Earth bulges at the equator, meaning the surface is farther from the center of the Earth at the equator than at the poles. A greater distance results in a weaker gravitational pull. Centrifugal effect. The Earth is rotating. This rotation creates an outward pushing centrifugal force that partially counteracts gravity. This effect is strongest at the equator, where the rotational speed is highest, and non-existent at the poles. Therefore, the effective acceleration due to gravity is slightly lower at the equator due to this outward effect. The value of g can range from approximately 9.78 meters per second squared at the equator to about 9.83 meters per second squared at the poles. For most everyday physics problems, we use the average value of 9.8 meters per second squared. This slight variation in g does not change the fundamental conclusion: at any specific location, all objects, regardless of their mass, share the exact same value of g, and therefore accelerate at the same rate. This uniformity in acceleration is the ultimate truth of the falling bodies problem. The physics is boringly consistent. The greater the pull, the greater the resistance, and the result is always a quiet, predictable rate of acceleration. We will continue the script now, focusing on terminal velocity in greater detail and calculating a specific example. Now let us focus exclusively on the condition of terminal velocity, the maximum velocity an object can achieve during its fall through a fluid like air or water. This concept is crucial for distinguishing between the idealized world of a vacuum and the complexities of the real world. As we established, terminal velocity, v sub t, is achieved when the net force acting on a falling object is zero. This occurs when the downward force of gravity, F sub g, is perfectly balanced by the upward force of air resistance, F sub d. F sub g equals F sub d. Or weight equals drag force. Let us express the drag force, F sub d, in a simplified form to illustrate the relationship. The full general formula for the drag force is F sub d equals 1/2 multiplied by rho multiplied by v squared multiplied by c sub d multiplied by a, where, again, rho is the mass density of the air, v is the velocity of the object, c sub d is the drag coefficient, a is the cross-sectional area. At terminal velocity, we can set the weight equal to this drag force formula and solve for the terminal velocity, v sub t. m multiplied by g equals 1/2 multiplied by rho multiplied by v sub t squared multiplied by c sub d multiplied by a. Now, we must algebraically isolate the term v sub t squared. We do this by multiplying both sides by 2, and dividing both sides by the product of rho, c sub d, and a. V sub t squared equals 2 multiplied by m multiplied by g all divided by rho multiplied by c sub d multiplied by a. Finally, to solve for v sub t, we take the square root of both sides of the equation. V sub t equals the square root of the quantity 2 multiplied by m multiplied by g all divided by rho multiplied by c sub d multiplied by a. This formula encapsulates the entire discussion on why objects fall at different speeds in the air. The terminal velocity is directly determined by the properties of the object and the fluid it is falling through. Notice the key ratios in the numerator and the denominator. The numerator includes the mass, m, which represents the gravitational pull. The denominator includes the cross-sectional area, a, which represents the object's interaction with the air. Terminal velocity is directly proportional to the square root of the mass, m. A heavier object has a higher terminal velocity. Inversely proportional to the square root of the cross-sectional area, a. A larger area leads to a lower terminal velocity. The combination of the two terms, m divided by a, is the mass-to-area ratio. It is this ratio that determines the maximum speed of fall in the real world. Consider two identical bowling balls. One is thrown into the air as a solid sphere. The other is somehow deformed into a thin, large, flat circular sheet with the exact same mass. The mass, m, and the weight, m multiplied by g, are the same for both objects. The solid sphere has a very small cross-sectional area, A. Its m divided by a ratio is very large. Consequently, its terminal velocity, v sub t, will be very high. The flat sheet has a very large cross-sectional area, A. Its m divided by a ratio is very small. Consequently, its terminal velocity, v sub t, will be very low. This is a demonstration where two objects of identical mass fall at wildly different speeds in the air, clearly proving that it is not the weight alone, but the aerodynamics that matters. The flat sheet must fall slowly to prevent the drag force from overwhelming its weight. The sphere must fall quickly to generate enough drag to match its weight. The classic example of the skydiver illustrates this perfectly. A skydiver typically falls in a belly-to-earth position with their limbs spread wide. In this configuration, they maximize their cross-sectional area, A. This results in a relatively low terminal velocity, approximately 55 meters per second or about 120 miles per hour. This is the speed at which their weight is balanced by the drag force generated by their large area. However, a skydiver can transition to a head-down, pencil position. In this position, their cross-sectional area, A, is dramatically reduced. Since the mass, m, remains the same, the m divided by a ratio increases significantly. To balance the same weight, a much greater speed, v sub t, is required to generate the necessary drag. Their terminal velocity in this position increases to 90 meters per second or more, allowing them to catch up to other divers or move more quickly through the air. And when the parachute is deployed, the parachute provides an enormous cross-sectional area, A. The m divided by a ratio plummets to a very small value. The new, much larger drag force immediately exceeds the constant weight, leading to a strong, immediate upward net force. The skydiver rapidly decelerates to a safe terminal velocity, typically around 5 meters per second, for a gentle landing. The parachute is not making the skydiver lighter, it is dramatically changing the air resistance term in the equation. This intricate balance between the unchangeable downward pull of gravity and the speed-dependent, shape-dependent upward push of air resistance is the true physics of falling in the real world. The simple answer is that the objects that fall fastest are those with the highest mass density and the most aerodynamic shape, the highest mass-to-area ratio. We will continue the script now, focusing on the experiment that finally proved Galileo's premise and the precision of modern tests of the equivalence principle. The most dramatic and conclusive demonstration of Galileo's principle was not performed on Earth, but on the Moon. In 1971, during the Apollo 15 mission, Commander David Scott performed an experiment known as the feather and hammer drop on the lunar surface. The significance of the Moon is that it has essentially no atmosphere, meaning the air resistance term, F sub d, is completely eliminated. The conditions were as close to a perfect vacuum as could be achieved in a practical experiment. Scott stood holding an 1.32 kilogram geological hammer and a feather from a falcon. He dropped both objects simultaneously from the same height. On Earth, the hammer would have struck the ground instantaneously, while the feather would have fluttered down slowly. On the Moon, both the hammer and the feather accelerated only under the influence of the Moon's gravity. Since the Moon is less massive than Earth, its acceleration due to gravity, g sub moon, is only about 1.62 meters per second squared, roughly 1/6 of the Earth's g. The mass of the hammer was 1.32 kilograms. The mass of the feather was nearly zero. According to the unified formula, A equals g sub moon, the acceleration of both the hammer and the feather was 1.62 meters per second squared. They had the same acceleration, a. The video footage of the experiment clearly shows the hammer and the feather falling in perfect synchronization, hitting the lunar dust at the exact same instant. This simple, public demonstration, televised across the world, provided the ultimate empirical evidence that mass does not influence the acceleration of a falling body in a vacuum. The cancellation of the inertial and gravitational masses was perfectly demonstrated. The hammer and the feather experiment is the most direct verification of the fundamental principle of equivalence in a real-world setting, far from the confounding effects of air resistance. The heavier hammer, with its greater weight, possessed a proportionally greater inertia, and the lighter feather, with its negligible weight, possessed a proportionally negligible inertia. The ratio remained constant. The hammer's weight on the Moon was F sub g sub hammer equals 1.32 kilograms multiplied by 1.62 meters per second squared equals 2.1 for newtons. The feather's weight on the Moon was F sub g sub feather equals approximately 0.001 kilograms multiplied by 1.62 meters per second square. Ed equals 0.00162 newtons. The ratio of the forces is massive, but the ratio of the accelerations is precisely 1. Acceleration subhammer equals F sub g subhammer divided by m subhammer equals 2.1 for newtons divided by 1.32 kilograms equals 1.62 meters per second squared. Acceleration sub feather equals F sub g sub feather divided by m sub feather equals 0.00162 newtons divided by 0.001 kilog. Rams equals 1.62 meters per second squared. This perfect equality is what modern science seeks to verify with ever-increasing precision. Tests of the equivalence principle are some of the most sensitive experiments ever conducted. These highly sensitive experiments utilize devices called torsion balances. A torsion balance is a very finely tuned instrument that consists of two different test masses, made of different materials like aluminum and gold, suspended from a thin fiber. If the gravitational acceleration were different for the two materials, if a violation of the equivalence principle occurred, the two masses would be pulled by gravity with slightly different forces. This force difference would cause the fiber to twist, or torque. These experiments have shown that the gravitational acceleration is the same for different materials to within a few parts in a trillion. For example, the microscope satellite experiment, a French-led mission launched in 2016, tested the equivalence of inertial and gravitational mass in the vacuum of space by measuring the acceleration of platinum and titanium test masses. It achieved a precision of 1 part in 10 carat, 15, or 0.0000000000000001. The result remains the same. The ratio of the gravitational force to the inertial mass is a constant. The heavy object does not fall faster because the two types of mass are one and the same. The realization that all objects fall at the same rate, often summarized as the equivalence of gravitational and inertial mass, leads us to a fascinating conclusion about the nature of gravity itself. We can now consider why this simple equality is so essential for the current framework of general relativity. In Newtonian physics, the fact that A equals G is a fortunate cancellation, a coincidence. In Einstein's general relativity, the equivalence is the entire structure. The core idea is that motion in a gravitational field is simply inertial motion, that is, motion not subject to forces, but within a curved space-time. Think of a pilot flying a plane. If the plane is flying straight and level, the pilot does not feel any push or pull. They are in an inertial frame of reference. They are simply following a straight path through flat space-time. Now, imagine the plane flies a curved path, perhaps a tight turn. The pilot and everything inside the plane feel an outward push, a force that changes their motion. The pilot is now in an accelerated frame of reference. Einstein's insight was that when you are falling freely under gravity, say, an astronaut in orbit or a person in a falling elevator in a vacuum, you feel weightless. This is the key. To an observer falling freely in a gravitational field, they feel no force. They are in an inertial frame of reference. The elevator, the person, and the ball they drop are all accelerating at the same rate g, meaning their relative acceleration is zero. They are all following the same curved path in space-time. This weightlessness, this absence of a felt force, can only be true if all objects are accelerating together at the exact same rate. If the heavier object were to accelerate faster, the astronaut would observe the lighter objects accelerating relative to them, meaning they would feel a force. Since no force is felt, the equivalence holds. The equivalence principle mandates that motion in a gravitational field is a universal property of space-time geometry, independent of the mass or composition of the object. All freely falling objects are simply moving inertially. To re-emphasize the role of the mass m in our formulas, it has two jobs. Job 1. Gravitational mass. This mass tells the gravitational field how hard to pull. F sub g equals m sub gravitational multiplied by g. Job 2. Inertial mass. This mass tells a force how much the object resists acceleration. A equals F sub net divided by m sub inertial. The experimental verification that m sub gravitational equals m sub inertial is why the gravitational pull cancels out the resistance to acceleration, leaving only the value of the curvature, g, to define the acceleration. The constant acceleration of g is essentially the measure of the intensity of the gravitational field at a specific location, or in Einstein's view, the rate at which spacetime curvature will deviate an object from a straight path. It is a property of the field itself, not the object. This is the power of the cancellation. It takes the specific properties of a falling object, its mass, out of the final equation for acceleration, unifying the motion of every object in the universe under the single umbrella of geometry. The physics is settled. In a vacuum, everything falls at the same acceleration. In air, the observed differences in falling time are due entirely to the interference of aerodynamics, the ratio of the object's mass to its cross-sectional area. We will continue the script now, focusing on a final practical example and summarizing the entire argument. For our final practical illustration, let us perform a detailed mental experiment on two objects of identical shape and size but drastically different masses, to isolate the effect of the mass term in the presence of air resistance. Imagine a solid iron sphere and a hollow plastic sphere. Assume they have been manufactured to have the exact same size and the exact same spherical shape. Because their shape and size are the same, their cross-sectional area, A, and their drag coefficient, C sub d, are identical. The iron sphere is much more massive, m sub iron. The plastic sphere is much less massive, m sub plastic. If we drop them in a vacuum, as we know, they would hit the ground at the same time with acceleration g. Now, we drop them in the air. The equation for their acceleration is A equals g minus f sub d divided by m. Since the cross-sectional area, A, and the drag coefficient, c sub d, are the same, the drag force, f sub d, will be the same for both objects at any given velocity, v. The drag force only depends on the speed, shape, and air properties. F sub d sub iron equals F sub d sub plastic at velocity v. However, the deceleration term, F sub d divided by m, will be different because the masses m are different. For the iron sphere, the mass m sub iron is large. The denominator is large. Deceleration term equals F sub d divided by large m is small. The acceleration a sub iron remains close to g. For the plastic sphere, the mass m sub plastic is small. The denominator is small. Deceleration term equals F sub d divided by small m is large. The acceleration a sub plastic is quickly reduced from g. The large deceleration term for the plastic sphere means it will reach a lower terminal velocity much sooner than the iron sphere. The iron sphere will continue to accelerate for much longer, falling faster and hitting the ground first. This confirms the entire premise of our segment. In the real world, the heavier object falls faster only because its greater mass allows it to better resist the same amount of air resistance. The air resistance term, F sub d, affects the less massive plastic sphere more significantly than the more massive iron sphere. The greater the inertial mass m, the less impact the air resistance has on the object's acceleration. This is why a person can be relatively aerodynamic but still have a high terminal velocity. They possess a high inertial mass m to resist the drag force F sub d. We have arrived at the end of this deep dive into the physics of falling. Let us summarize the core argument one final time. The question why don't heavier objects fall faster is the wrong question. The correct question is, why do all objects accelerate at the same rate in a vacuum, and why do only some objects reach terminal velocity quickly in the air? The answer to the first part is the equivalence principle. The gravitational mass, which determines the pull, is perfect. Lie equal to the inertial mass, which determines the resistance. They cancel out, leaving acceleration a equals g. The answer to the second part is the mass-to-area ratio, the rate at which an object's acceleration is reduced from g by air resistance is directly proportional to its surface area and inversely proportional to its mass. Objects with a high mass-to-area ratio fall fastest in air. This is the harmony of classical mechanics and the profound starting point of general relativity. The boring physics of falling bodies reveals a universe of perfect, constant balance. We will continue the script now, focusing on a final summary and concluding remarks. The next segment will bring the total word count to 14,000 words, and the final segment will bring the total to 15,000 words. The journey from a simple observation, the stone falls faster than the feather, to the deep physics of space-time curvature is complete. The beauty of this subject lies in how a simple experiment performed in a vacuum chamber or on the surface of the moon can reveal a truth so fundamental it is woven into the geometry of the universe. We have used only 3 core concepts, which are worth reviewing one final time for maximum retention. The 3 core concepts. 1. Force of gravity, weight. The pull is proportional to the mass. F sub g is proportional to m. F sub g equals m multiplied by g. Heavier objects are pulled harder. 2. Inertia, resistance to acceleration. The resistance is proportional to the mass. Resistance is proportional to m. A equals F sub net divided by m. Heavier objects resist changes to their motion more strongly. 3. The cancellation in a vacuum. The proportional pull and the proportional resistance are exactly equal, leading to a perfect cancellation of the mass term m in the acceleration equation. A equals m multiplied by g divided by m equals g. Acceleration is the constant g, independent of mass. The interference of air resistance. Air resistance, F sub d, introduces complexity in the real world. The total acceleration is always trying to be g, but it is reduced by the effects of the air. A equals g minus F sub d divided by m. The term F sub d divided by m is what creates the difference in falling times. The smaller the mass m is, the larger this reduction in acceleration becomes, causing the object to reach a low terminal velocity. The larger the mass m is, the less effect the air resistance has. Terminal velocity is achieved when m multiplied by g equals F sub d. V sub t is proportional to the square root of the ratio m divided by a. The fastest falling objects in air are those that are dense and have minimal cross-sectional area, maximizing the mass-to-area ratio. The study of this phenomenon is not just historical curiosity, it is the cornerstone of several modern engineering and scientific disciplines. In aeronautical engineering, the entire design of aircraft and spacecraft relies on a precise understanding of air resistance and terminal velocity. The maximum speed a skydiver can reach, the speed at which a meteorite will impact the Earth, and the efficiency of a wind turbine blade are all governed by the drag equation and the mass-to-area ratio. In particle physics, the equivalence principle is a key test for theories that attempt to unify gravity with quantum mechanics. Any new theory of physics must, at the minimum, explain why the gravitational mass and inertial mass are so perfectly equivalent. The slightest deviation from this A equals g principle would point toward new, currently undiscovered forces or particles. The history of this one concept is a history of physics itself, a perfect narrative arc from assumption to experiment, from observation to mathematical law. The simple act of dropping two objects has led us to the edge of theoretical physics. Close your eyes now and let the perfect, constant acceleration of 9.8 meters per second squared wash over you. The physics is predictable, the concepts are clear, and the world is in balance. This is the final segment of our script, bringing us to the requested total word count. Let the stillness of the concepts guide you to rest. The final element to consider is the subtle time dependence of the falling motion in the presence of air resistance. A full analytical solution for the motion of an object falling in air is complex, often requiring differential equations. However, we can visualize the relationship between velocity and time for our two object types, the dense sphere and the light feather. If we plot velocity on the vertical axis and time on the horizontal axis, the slope of the curve at any point represents the acceleration. In a vacuum, the graph for both objects would be a straight line starting at velocity 0 and increasing with a constant slope of g. Velocity equals g multiplied by time. V equals g multiplied by t. The final velocity, v sub final, at the moment of impact is simply v sub final equals g multiplied by t sub final. In air, the graphs for both objects start with a slope of g, as the initial velocity is 0, and through s the drag force F sub d is also 0. A sub-initial equals g minus 0 divided by m equals g. As time, t, increases, the velocity, v, increases. This causes the drag force, F sub d, to increase proportionally to v squared. The drag force in turn reduces the acceleration, causing the slope of the graph to curve downward. For the light feather, the mass m in the denominator is very small, so the initial acceleration quickly drops. The curve flattens out almost immediately, becoming a horizontal line at a very low terminal velocity, v sub t sub feather. The slope, or acceleration, quickly becomes zero. For the dense sphere, the mass m in the denominator is very large, so the reduction in acceleration is gradual. The curve is a gentle slope that continues upward for a long time, approaching a high terminal velocity, v sub t sub sphere, only after a prolonged period of fall. The entire difference in the real-world falling time is encapsulated in these two curves. The feather stops accelerating quickly due to its low mass, while the sphere continues to accelerate for much longer due to its high mass-to-area ratio. The final message of this segment is the recognition of the constant tension between the universal truth of gravity and the local conditions of the fluid through which motion occurs. Gravity provides the constant, mass-independent acceleration g. Air resistance provides a counter-acceleration that is entirely mass-dependent through the inertial term m. The formula that governs the final speed of any falling object in the atmosphere, the terminal velocity, is the algebraic expression of this balance. V sub t equals the square root of the quantity 2 multiplied by m multiplied by g all divided by rho multiplied by c sub d multiply by a. It is the density, the shape, the size, and the mass working in concert. With this final formula, we have reached the conclusion of this discussion on why heavier objects do not fall faster. The physics is precise, the formulas are clear, and the fundamental laws of motion hold true across the cosmos. We thank you for tuning into Boring Physics for Sleep. Good night.